It's pretty sigma, but not like that. No. Sigma notation, one of the many topics I'm going to cover in this video. The entirety of algebra, not really, explained in 15 minutes, part 1. Let's go! We start by counting. Humans have 5 fingies on each hand, which makes it easy to count from 1 to 10. But what's not easy is negative numbers. Negative fingies, which is just painful and not a good way to introduce these numbers. So instead of amputation, we resort to a line, a road that spans infinitely far in the positive numbers and infinitely far in the negatives. Great, you have unlocked the number line. So if you were to choose a random number in this set of numbers, x, then you would most likely get a never before seen value that will never be written down ever again in the entire existence of the universe. Anyway, what is x? X is a variable, an object in which values can be stored. Algebraic expressions, which are basically quirky little math statements, always have variables. When you see something like this, it is saying that there are 2 lots of the value x. The coefficient of x is 2, so it's just x times 2. It is the same as x plus x, but not x times x. That is x squared. But why do we call it squared? Well, imagine x is the side length of a square. We know all squares must have equal sides that are perpendicular. Given that x is one length and all lengths are equal, we know that all lengths are x. We also know that the area of a rectangle is the length of the perpendicular sides multiplied, so the area of a square is x times x, x squared. Awesome, now you know what a square is. But when we look at this, what the flip? Dude, what the flip?
What the flip?
Is the 2. Well, it is the exponent, a value that makes straight lines go like this. Straight lines, when graphed, are lines made by the equation y equals mx plus c. Or b if you're feeling extra quirky.
The animatronic characters here do get a bit quirky at night.
This equation and every other 2D graphable equation is asking, when x is equal to something, what is y equal to? So when you are graphing it with Desmos, the program is finding y, like me, find y, join the Discord server, for every possible x value. I mean, that's great for stuff like y equals x, but what about these other things? M stands for Minecraft.
Depends on the whoa, hey.
No, it doesn't. M stands for the slope, the steepness of the graph. So when we are multiplying x by m, it is setting the steepness of the graph. And finally, for the B, C anemone. C is the y-intercept, the y-coordinate where the y-axis and the line meet. So, to quickly recap, for each possible x-coordinate, the respective y-coordinate is equal to the steepness multiplied by said x, then shifted up or down by the y-intercept. Bed Wars. Bedmass,
PEMDAS, 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 PIDMAS, PEMDAS, BOMDAS, GODMAS.
All stupid acronyms that mean the exact same thing. In expressions, the calculation process is brackets comes first, then exponents, then multiplication, then division, then addition and subtraction. But what does it mean for brackets to come first? Well, it depends if the expression has unknown variables within the brackets or not. For an expression like x 5 plus 6, you would add the known values within the brackets, then expand it by multiplying it by x. But for something like x 5 plus y, we can't add 5 to y at the start because we don't know what y is. So we just do the expansion to get 5x plus xy. This is known as expanding single brackets. I mean, but what about double brackets, triple brackets, tetra brackets, skibbity toilet brackets? In all expansions, we are multiplying everything on the outside by everything in the inside. One of the easiest methods is a thing called FOIL. First, outer, inner, last. For something like x plus 1, x plus 2, you multiply the first by the other first, x times x, then add that to the first times by the outer, x times 2. Then add that by the inner times by the other first, 1 times x, and finally add that to the outer times by the other outer, 1 times 2. And you get something like this. Now this, remarkably, preposterously, absurdly, incongruously, is crap. It's crap because it ain't simple, I mean that's obvious, but one of the big parts of basic algebra is the process of simplification. It makes your life easier while solving equations because it turns an expression into the most efficient and smallest it can be. But you know what else makes your life easier while solving equations? Today's sponsor, Brilliant.org. pain comes in many forms. If you're anything like me, getting a well-deserved not achieved in arithmetic is not a great feeling. With Brilliant's vector, measurement and geometry, and predicting with data courses, I went from being a doomer to a doomer with more of a clue than usual. That sounds great. It is great. Doing Brilliant for even a couple seconds a day won't help, but doing Brilliant for a couple minutes will. Problem-solving skills are built up through the hands-on math and science lessons, which are 6 times better than watching lecture videos and much better than pure memorization. I know that because I can't remember anything. I know that because I can't remember anything. I know that because I can't remember anything. Have you ever wanted to know how NPCs work? Bam! Multiple courses on AI and large language models. Want to know how your passwords and home security work so you can protect yourself from Vsauce? How technology works is the course for you. So if this sounds mildly delectable, to try everything Brilliant has to offer for free for a full 30 days, use my link, brilliant.org/findwhy. You'll also get 20% off an annual premium subscription. Returning to the expression x squared plus 2x plus 1x plus 2, we simplify it down to x squared plus 3x plus 2. What we did is we separated each term from each other based on coefficient and exponent, then added it together. We never properly went over powers and exponents, so let's do that. When you're dealing with powers and roots, there is the coefficient, which you always deal with first. Then there's the base and the exponent. If the bases are the same, we add powers when multiplying bases and subtract when dividing. So for that expression, as I said, you deal with coefficients first, 12, then add the powers. So in the end, you get 12x to the power of 3. If an equation has identical bases and coefficients on both sides with the equal sign, then the powers must be equal. This is very helpful in doing basic exponent problems. Yeah, I'm yapping on about stuff that is equal, but what if it's unequal? An inequality or inequation. This means less than, this means greater than, this means less than or equal to, and you guessed it, this means greater than or equal to. Equal to what? Any number or expression that fits on our good old pal number line. It'll tell you a range of possible x values in cases like -6 is less than x is less than or equal to 2. And this is saying that x is a number between -6 and 2, including 2. It's important to note that when solving inequations, if you divide or multiply both sides by a negative number, the sign flips. This also happens when taking the reciprocal. This all seems to take a lot of time to solve, so what about something that happens all at once? Simultaneous equations. Well, actually, they still take a lot of steps, and it's probably more than the other ones, but shut up. Shut up! This is a system of equations. A set of equations with more than one unknown variable, which we solve for simultaneously by working on both at once. There are 2 techniques for solving these: elimination and substitution. For this example, we multiply the entire top equation by 5 and multiply the bottom by 2. This makes the y coefficient for both equations the same, and thus we just subtract them from each other to get rid of, defenestrate, if you will, the y variable. We are left with 23x equals 29. Divide both sides by 23, and you get x equals that crap right there. Launch that back into the simplest original equation, which in this case is the top one. Do the math and then solve for y. 2y equals that stuff, therefore y equals that. These are the chords for where the 2 lines confront each other. For this next part, you gotta log in. Yeah, it's like lock in, but like log-lin, natural log. Enough with the shenanigans, we don't have time here. Logarithms, trees that like music. They are the opposite to exponents. I mean, they're not roots, but what they do is they find which power a base has to be raised to equal a number. It is written like log 2 of 8 equals x. This is saying that 2 to the power of x equals 8, therefore x equals 3. When you just see log of x equals y, it is saying that 10 to the power of y equals x. You see, the 10 drank an inverse pot and is just cool like that. They are useful. Imagine you had 2 to the power of x equals 16. Now, because you guys are big brain, you'll quickly see that x equals 4. But let's imagine you have the same IQ as my dog. I don't have a dog, so you really don't have any IQ. First step is to take a log of both sides. Log of 2 to the power of x equals log of 16. Now this next step involves something called the power rule, where the exponent of the number in the brackets can be moved outside of the log and become a coefficient. Now that you have x times log of 2 equals log of 16, we can divide both sides by log of 2 to make x the subject. x equals log of 16 divided by log of 2. This is the same as log of 2 to the power of 4 divided by log of 2. And if you apply the power rule once again, we have 4 times log of 2 divided by log of 2. Now, anything divided by itself that is non-zero will equal 1. So this is saying x equals 4 times 1. In other words, x is 4. Yeah, okay, cool, but what about natural logs? The natural log of x equals y only if e to the power of y equals x. E, like random Lord Farquaad Markiplier meme from 2018. Yes, that's the one that mathematicians named the number after. And it's roughly equal to 2.718. The natural log of 1 equals 0, and the natural log of e equals 1. There is a thing called the product property, which applies to both natural and normal logs, that pretty much state that the natural log of x times y equals the natural log of x plus the natural log of y, and same goes for the opposite, division. So the natural log of x divided by y equals the natural log of x minus the natural log of y. Now let's say that the natural log of x equals 3. This is saying that x equals e to the third. So you literally just raise 2.718 to the third, and you get x equals roughly 20. It's not that deep. Now at the start of this video, I did promise to cover sigma notation, and I'm gonna be honest, this section's gonna be pretty nonchalant. What the sigma is sigma.
No, alright. I know that sounds bad.
It is a Greek letter that mathy boys use as the notation for summation. The total you get from adding together all numbers in an iterative sequence. There are 3 inputs, the thingy at the top, A, the thing on the right, I, and the thing at the bottom, B. With the current conditions, this expression is saying that as I increases from B to A, counting up one at a time, add the numbers together. So let's imagine that A equals 5 and B equals 1, and we keep I as it is. It produces 1 plus 2 plus 3 plus 4 plus 5 equals 15. Now the special part is that when we change the I on the right to something more goofy R, for instance, I squared plus 5, now if we keep the other parameters as they were, 6 plus 9 plus 14 plus 21 plus 30 equals 80. Now there are a couple useful common formulas that revolve around summation. This one gives us the sum of all the natural numbers, so positive integers, from 1 to n. So if n equals 50, you are adding 1 plus 2 plus 3 plus 4 plus 5
plus 6 plus 7 plus 8 plus 9 plus 10 plus 11 plus 12 plus 13 plus 14 plus 15 plus 16 plus 17 plus 18 plus 19 plus 20 plus 21 plus 22 plus 23 plus 24 plus 25 plus 26 plus 27 plus 28 plus 29 plus 30 plus 31 plus 32 plus 34 plus 35 plus 37 plus 38 plus
90 plus 50. Now that would be very painful. Had this formula not existed, simply plug 50 into n, and we get 1,275. A good old jolly old chap, Bernard Riemann, was playing some Go Fetch with his dog, and whenever he threw the ball, he noticed it traveled in a curve. I have talked about finding the area under a curve in my calculus for Gen Z part 1. Yeah, there's going to be more to come, go watch that. Yeah, but this guy took a marginally different approach. So imagine you have the curve formed by negative x squared plus 1, and you're Riemann, and you're looking for a way to find the area under this curve between 2 x values. This range is called the interval. It is a closed interval, so it includes the 2 numbers themselves. And we begin by dividing this segment of the x-axis into parts. The amount of parts that you divide it into, the more accurate the area will be. Let's say that you divide it into 100 subsections, or sub-intervals. So delta x equals point B minus point A divided by n, where n is 100, and point B is the greatest number out of the 2 points. Now we have to have a value within these sub-intervals that we use to calculate with. Most commonly, this is the midpoint. This little fancy thingy here is the midpoint for a given sub-interval, and it is equal to xi minus 1 plus xi divided by 2, where the other xi things are the left and right points of the sub-interval. Man, this has to be the most amount of yapping I've done on this channel. Well, you think I'm gonna stop? No, of course not. We plug this value along with our original sub-interval calculator into this sum, and what we have is an elegant equation that, if we wanted to manually add together, would make me cry myself to sleep even with that thingy under my bed. And in fact, that thing is so scared of having to add 100 sub-intervals together after substituting them into negative x squared plus 1. So we resort to the next best thing after Desmos fails to do its job. It's definitely me just being dumb. And get GPT to do it for us. And what do you know? 1.33 recurring is the area, and when we plug the function into a definite integral, we get the same answer. But find y, my beloved. Where is the abstract algebra? The linear algebra? The real analysis? Where is my vertex operator algebra? Whatever the hell that is. Okay, I lied. This video does not cover all algebra. But I do want to cover at least some of it, so if you guys actually found this video remotely useful, and if it gets more than 3 views, I'll consider upping my game for the next one. But until then, catch you later. Thanks for watching. This video is so bad, like, actually. Like, how am I gonna edit this? This is ridiculous.